So more on continuity. Not too big a lesson here, but one big idea that you need not be scared of because I'm just introducing the big idea and we'll have to use it more as the course goes along. So here's some properties of continuous functions. These are all great news. After sine and cosine and logs that were very tricky rules about how you could combine functions and how you could add functions and all those type of things, continuous functions are nice. If two functions are continuous at a certain value, at x equals c, then their sum will be continuous. So if you add two functions together and they're continuous at a point, they stay continuous at that point. If you subtract them, if you multiply them, any of those things are totally allowed and you'll stay continuous. You can also multiply it by a constant. They use a k here. Lots of times we use a c in these type of notes, but they use a k here to say if there's a constant up front, it stays continuous. And quotients are continuous. So two continuous functions, their quotient will be continuous unless the denominator happens to be 0 there. Okay, and I'll show you what I mean by that on this very first function. Show that the function y equals x sine x is continuous, x sine x over e to the x plus 2 is continuous for all values of x. You're going to think I'm overkilling this thing. I'm going to show all the individual steps. I'm going to show off all this stuff here to show how nice the rules are. Y equals x is continuous. It's a polynomial. Right from the beginning of polynomials, we never worried about continuity back then. We knew we could plug in any x value to a polynomial and get a y value back. So y equals x is a polynomial, or sorry, is a continuous because it's a polynomial. Now, if you're wondering where I'm going with this, it starts to fall into place in just a second. Y equals sine x is continuous. We know that for sure after our study of sine x. It was periodic in nature. It just kept going, and there was no gaps, no holes, nothing. Still confused about where I'm at. Here's the big moment of this example. Therefore, y equals x sine x is continuous. And I'll get really formal here and I say, because a product of continuous functions is continuous. So you see what I'm up to? I'm slowly building this crazy function here. I said, okay, one piece at a time. X is continuous. I know that because it's a polynomial. Sine x is continuous. So x sine x is continuous. I'm done the numerator. The numerator's always continuous. Next, the denominator. Y equals e to the x is continuous because it's an exponential. Exponentials are continuous. And just in case e to the x, I know e to the x is new this year, so just in case e to the x is like, I don't even know what e to the x looks like. It just looks like all the other exponential functions. But the base is e now instead of 2 or 3 or something like that. So it just looks like that. So that function clearly continuous. Therefore, y to the e at x plus 2 is continuous. Because I'm just adding 2 on there, and 2 is clearly a continuous function. E to the x is continuous, so e to the x plus 2 is a continuous function. See, I'm building, I'm on my way. And if you're really with me, you're like, wow, you are really building. You're really taking it down to the very little tiny pieces. I've taken each individual function in this crazy function, and I've proved each piece is continuous. Now my important second last line. Therefore, y equals x sine x over e to the x plus 2 is continuous because it's a quotient. Of two continuous functions. Let me review the whole lesson so far. X was continuous, sine x was continuous, numerator was continuous, e to the x was continuous, 2 was continuous, e to the x plus 2 was continuous, denominator was continuous. Now, that means x sine x over e to the x plus 2 is continuous. But I've missed one little thing that I want to spend just a moment on. What little thing did I miss? How could this function slip through the gaps? There's one little moment I've missed. Yeah, so let me just move this out of the way, my little recording box for a second. Okay, that's right. I'll put this here unless e to the x plus 2 equals 0, question mark. One last little thing. Make sure you didn't throw a denominator equals 0 there. And Ethan's already said e to the x plus 2 can't equal 0. So I'm looking for two explanations. The graphical one, which is nice. We love the graphical one here. And then the algebraic one, which might not cause you a little headache, but you should see. What's the graphical one? Or
It has an
yeah, never going to reach 0. And it's even better. It's moved up 2. Yeah, so it's even better than that. E to the x, we were already there. If it happened to move down 2, then we might get a 0 out of this. But this is moved up 2. So a quick graph to convince you graphically that we're okay here. 1, 2. Little asymptote there. And n e to the x. So that graph is supposed to convince you that e to the x will not, or e to the x plus 2 will never equal 0. This denominator won't be 0, so I'm okay. But I want to do it algebraically as well. Okay, e to the x plus 2 equals 0. E to the x equals negative 2. At that point, you might be convinced already, but ln. You're like, oh, ln. Okay, ln. Let's just go through ln again. All right, adding, subtracting, subtracting, adding, multiplying, dividing, dividing, multiplying, squared, square root, square root, squared. We had all these inverses. Inverse of e is ln. When you move e to the x over, it becomes ln. And then ln of negative 2, no real answers. Just like square root, you can't do lns of negative numbers. So that's how you would do it algebraically. Am I setting up for an algebra question like that? No, not necessarily, but I just wanted to mention that this could be done algebraically. There's no reason to rely on the graphical version of that, especially if the graph got complicated. This was a nice, easy graph. Okay, any questions about that? George is like, get out of my picture. I'm only 4 slides, am I right? Or 4? Oh no, it's 4 to me. It's not necessarily 4 to you. Okay, never mind. Questions though? Your chance to be on a video for the next 20 years? Composition of continuous functions. Put this up here now. If f is continuous at c and g is continuous at f at c, then the composite is also continuous. Mr. Todd, I don't remember composite really. Okay, here's a tiny lesson on composite functions here. It says express this function as a composition of 2 functions. It said 2. I could make it a composition of several. 2 works good because does the inside look familiar at all from what we were just doing? Controller. Oop, wrong spot there. X sine x over e to the x plus 2. On purpose, on the second example, I'm using the first one right in there. So here's composition, taught a different way than last year. So maybe if it wasn't clear on what composition is, now it will be clear. So I'm going to let g at x equal x sine x over e to the x plus 2. See, I've let g at x equal the inside part of this. See, just about every function we've looked at over the years actually was a composition of functions, but we didn't call it that. What a composition is, there's a function, and then there's an outer function that has to operate afterwards. So the inside, I'll call g at x. Certainly. And then I'm going to let f at x equal absolute value of x. Now, let me just re-explain that. I've said, okay, let the inner function be called g, let the outer function be called f, and therefore f of g, some people say fog when they're first learning it, they call it fog. It just means f with g at x inside it equals x sine x over e to the x plus 2. So explained that way, it might be like, so there's just one function inside another function? That's all fog is? Absolutely. And it's not really clear why we would need composition of functions, but it's coming right up. Very close now. We're days away from derivatives. It's so exciting. Changing your math life, coming right up. Yeah? Oh, I did it. Oh, I'm done. I didn't realize A was all it asked me to do was express as a composition. I just said, okay, the inner one I will call G. The outer one I will call F. And so f of g is f at g at x, f with g buried inside it, that's composition. And right now you can be like, all right, so you just called them different names? That's what you did? I'm like, yeah, just called them different names because we're setting up for some stuff. All the pieces are in place now, finally. Tomorrow, derivative. Well, starting with derivative. Derivative. Is the function continuous at all values of x? Explain. Okay. G at x is always continuous. See previous example. I just proved that in the previous example. F at x is always continuous since f at x equals absolute value of x. We know that's continuous. Here's the quick graph of absolute value of x. Big. And so my less than dramatic final conclusion, therefore f at g at x equal to absolute value x sine x over e to the x plus 2 is always continuous. Mr. Todd, why do we care if they're always continuous? Oh, it's going to be a side thing. A whole bunch of work we do over the next few months. It's going to be, well, as long as it's continuous, we can do this. And then it's like every day it's going to be seem like that. Everything I do, I'm going to, well, as long as it's continuous, we can do this. So it's important for us to know what continuous is, even if it's pretty straightforward. Even if you're like, well, this continuous thing, I think we already sort of knew what continuous was before you did your 2 fancy lessons on continuous. So that's okay. Any questions there on composition of continuous functions? More time? Georgia, question. And now you're on the video forever. Oh, it's going to be good. We got about 3 months of math that every day I'm going to finish and you're like, so that's all? That's what you do? All right. Now, the algebra is going to be complicated, but if you made it this far, you're probably very good at algebra. Collecting like terms, multiplying out brackets, factoring, those type of things. The algebra might be a little challenging for a while, but the ideas won't be. The ideas of calculus are not that bad. They're so powerful. You know, it's going to be back to 2 to 2.1, 2 to 2.01 thinking without all the work. I'm giving it all away. I'm excited. It won't be hard for me to get out of bed in the morning for the next 6 weeks. We're like, going to teach calculus. You know, you're right. It will not be overcomplicated. The algebra might be. Fair warning. The algebra might be. Okay. More time here? Oh, this is big. So simple and so powerful. But again, this intermediate value function that I'm going to talk about here, or the intermediate value theorem, we're just going to dip our toe in it today. All right? So if my explanation I do next is a little bit out there, don't freak out. This is like the first time I mention it. There's 2 full lessons in this course where I just spend the whole day talking about this. So we're not getting crazy here. I'm just touching on a little idea here. And I'll explain the little idea before I begin. I argue that if you've got some function that has to go from 2 up to 7 in its y values, it has to touch every number between 2 and 7. Eventually, it touches every number between 2 and 7. If it's continuous. If it's continuous. There, that's the end of the story. This is the fancy version of it. A function is said to have the intermediate value property if it never takes on two values without taking on all the values in between. And they make it look really fancy, but it's as simple as what I just said. If you want to go from 2 to 7 and you're continuous, you've got to touch every number between 2 and 7. So a function y equals f of x that is continuous, see, this is what I was talking about. Like a whole bunch of stuff we're going to do the next little while. It's going to say, well, as long as you're continuous, this is true. So we got to know about continuity. On a closed interval, takes on every value between f at a and f at b. So no matter how you want to get here, if you want to get from this y value up to that y value, you're going to have to touch every single y value in between to get there. If you're continuous. If you're not continuous, you can do whatever you want. But if you're continuous, you've got to hit everything. In other words, if y0, this y0, is between f at a and f at b, then at some c, it's going to hit that. That's the fancy way of saying that. At some c, you're going to hit that y value. Why do we care? Well, actually, stepping way forward, it has to do with existence of solutions. Sometimes we can't solve an equation, but we know there must be a solution out there. Then we can set a computer to work on finding the solution. Okay? We need to first establish, does there have to be a solution? And if this low value was 2 and that high value was 7, and we wanted to find out when it was 4, we know there's a solution. We know it's out there even if we can't find it just yet. All right, that's jumping way ahead. That's like, that might be March type thinking, okay? Long way to go to there. Last example, am I right? Last example. Use a graphing calculator. Determine if any real number is exactly 1 less than its cube. And I'll do the second sentence after I do that. Well, at first glance, this might be a little bit of trouble, but let me just write a couple things. Let x be any number. Therefore, x cubed is the cube of that number. Questions like this boggle people's minds because they don't know to write down those first two sentences and then read it again. See, I didn't really read it the first time. I don't even remember what it says. All I saw was a number and its cube. And I was like, oh, hold on. I'm going to read it again after I go, let x be a real number, and x is the cube of that number. Now I can read the sentence again and find out what's going on. Determine if any real number, x, is exactly 1 less than its cubed. There. See, once I have that weapon there where I've stated what the variables are and what they mean, then reading the question again allows me to easily come up with an equation. Use a graphic calculator to determine if any real number is exactly equal to 1 less than its cube. Now I'm in great shape. I don't know why it's mentioned in graphing calculator, but here I'm going to go after solving this. Move the x over. 0 equals x cubed minus x minus 1. Let's do the factoring from yesterday. Looks pretty straightforward. Sub in, let p at x equal x cubed minus x minus 1. P at 1 equals 1 minus 1 minus 1 equals negative 1. Well, that didn't work. P at negative 1 equals negative 1 plus 1 minus 1 equals negative 1. And Mr. Todd said if it didn't divide into the negative 1, it wouldn't work. It doesn't factor. Uh-oh. Yeah, that's why it says use a graphing calculator. Here's one that doesn't factor. And might scare you a little bit, like, wait a minute. We went through a whole course where all these things you gave us factored, making me believe that factoring was the way to solve equations. And that's true, unless it doesn't factor. It's not a quadratic, so the quadratic formula is out. Is there a cubic formula? Well, yes, there is. Let's take a look at it. The cubic formula. No one, just to be clear before I put it on the screen, no one ever uses it. But it exists. There's somebody out there who had just enough time to come up with a formula for cubics. The cubic formula. Remember x equals negative b plus or minus square root of b squared minus 4ac? There's the cubic formula. Oh, it's way worse than it looks. Look at this mess. Georgia wants in. She's like, okay, here we go. I'm in. My kind of deal. So there is a cubic formula, and higher degrees are just going to get more complicated. These are not the type of things we use all the time. It's nice. The quadratic formula is nice, but we're not using a cubic formula. To which you might be like, well, so a very basic cubic equation, and we can't solve it. No, we can't. We need the derivative. Yeah, let's get the derivative done. And then when we come back to this type of problem in March, we'll be able to do it. Yeah, okay. For now, we use the graphing calculator. Okay, so the story's not over. Long way to go. Graphing calculator. What am I going to do here? What am I going to do here? Several choices. I'm going to let y equal x cubed minus x minus 1 and solve for when y equals 0. That's a pretty clever way to handle this situation, to solve an equation. Let it equal some function, and then solve for its 0. So when I go to graph this thing, I'm going to put in x cubed minus x minus 1. Before I hit draw, is there going to be an answer? Does there have to be somewhere where this thing is equal to 0? That's what the question's asking. Is there? It didn't ask what the real number was. It says determine if there's a number that equals 0. Does this function have to have a 0 before I press graph? Georgia. Yes, she says. Why do you say it has to work out that way? Well, hold on. It's continuous. So it takes on every value between any two values. Yes. Oh, the dancing's back. Homecoming dance coming up, right? So don't be nervous about going to the homecoming dance and looking silly out there, because you won't. You've got moves available. Right? Don't forget the asymptotes. Tell me about the end behavior. Yeah, it's like this. And so the intermediate value theorem immediately says, you got to hit 0 at some point. If you're going to start here and there, you're going to, okay, I've already answered the other question. It's going to work. Draw. There it is. Why it was so hard to find is that it is a decimal. So I'm going to use gsolve, find the root, and I get 1.32. X equals approximately 1.32 from the graphing calculator. And George has already answered the other question. What is the significance of the intermediate value theorem? Since degree 3, positive leading coefficient has end behavior. That'll be the name of your dance. We're doing the end behavior. It's going to take over the gritty. Is it gritty? Am I using that word right? X goes to infinity, y goes to infinity. X goes to negative infinity, y goes to negative infinity. Which Georgia carefully put into a dance. Listen, just draw that, will you? That's what you got to draw. But here's what. Just in case you're still nervous about the dance. That's what you're looking for there. Call it the infinity dance if you want. That sounds cooler. Oh, no, I got to finish my thinking. Since degree 3 leading coefficient has n behavior, blah, 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 the intermediate value theorem says y must equal 0 somewhere. It's an existence theorem, we call it. We know there's an answer out there somewhere. And then the challenge will be to find it. We don't want to be looking around for solutions that don't exist. Now we'll have a method called Newton's method, if you're dying to look it up. Newton's method will allow us to find these things once we have the derivative. So that's where we'll turn our attention for a couple of months, actually. Any questions about that last example? We used that last year. Remember those crazy questions where it's like, does a cubic have to have, what's its minimum number of zeros? We said, oh, it has to have a 0. We were using the intermediate value theorem, but we didn't know it. Oh, wait. Oh, I was going to stop recording. Okay, okay.